Hi, welcome back to McClatchy Maths. My name is Natalie McClatchy and we are continuing our video series today on the 2024 external exams for Queensland, Australia for general mathematics. And our focus today is on paper 1. We're looking at short answer questions by Bivariate data analysis. These questions require you to show all your working, and also there are marks allocated for those steps in between. Well, before we get going on that, I want to tell you a little bit about how you can engage further with me here at McClatchy Maths. Firstly, like and subscribe to the channel. Tell someone about the channel by putting it in your OneNote or even sharing it with the little arrow button. You could even tell us in the comments if you found the video helpful or we saved your bacon the night before the exam. And if that's the case, why not say thanks in an even more meaningful way? You could hit that little love heart button and donate $2 using your PayPal account, which is very secure, but it also enables us to continue producing videos for the channel as there is a cost involved. Right, let's get on with our first of two questions, question 19. The table shows data from a mobility test that counts the number of times a person can stand from a seated position in 30 seconds. So I've got the first line of the table is somebody's age, from age 50 up to age 90. And then I've got how many stands they can do in 30 seconds. And obviously as they're getting older, then they're able to do less and less. Now this is a 4-mark question. Part A is worth 3 marks. So this is where we really want to do well. We have to construct a scatter plot to display the data on the grid provided. Now, drawing a graph, this is basically year 7 skills for graphing, but we need to have a think first about which of these is going to be my explanatory variable and which of these is going to be my responsive variable. Which one is going to have an impact on the other? Well, I would venture to say that how old you are has an effect on how many stands you can do. Obviously, as we get older, we become less flexible. I know that from personal experience. And that means our fitness can diminish over time. Now, it's not always the case. Sometimes there are people in their 90s that could bench press far more than I could in my 20s. But in general, most people's ability to do physical activity declines as they get older. Okay, so we've identified that explanatory variable. That's what we're going to be graphing on the x-axis, person's age. And so what I'm going to do here is I'm going to start using the graph paper that was provided, and I'm going to start at the number 50. I could start at 0, but my data starts at number 50, so that's where I'm going to start. And because I'm doing that, I should put this little lightning bolt or a little break in the axis. If I don't do that, what I'm saying is that there's a jump of 0 to 50 here. 50 years is represented in that space, which is not technically correct if I then use the same size space to jump up in 5-year blocks. So I put the break in there and that saves me. And I need to label my axes as well, put a title on my graph. These are all basic skills you know about graphing. Notice I've started this one here at number 8. I could have started once again at 0 down the bottom, but if I've put a break in the axis down here, I can cut across that little corner and have a break in both axes, and it makes it much more efficient for graphing. Okay, so let's graph our first point. It's 50-20. Our next point is 55-18. 60-16. Now I need to be really careful that I'm putting these exactly in the right spots, not off away from where the little lines cross over. I need to make sure that I've graphed them perfectly because I'm going to be marked on that later on. So now I've put in the next point, the 5th point, 6th point, 7th point, and the final point here. Okay, so I've constructed my scatter plot. Now here's where these 3 marks were allocated. Oh, there's my last point there. Okay, firstly, putting age on the correct axis. So if I got these flipped around, I'm going to lose a mark. I don't want to do that. So make sure, and they've even made it really nice for you. They've put the X variables first, which is typically where we would do that in a table. So making sure we do that carefully. Accurately plotting those points based on which axis we used. So if I had switched these 2 around, I could still get the mark here. And thirdly, formatting the scatter plot properly. So we're looking at the axis titles. That's these ones here, and I've written those down. And also this here, the correct scaling. Remember how I mentioned the little break in the axis? If I don't do that properly there, I would probably lose that mark there. So I want to make sure that I've indicated that I'm breaking. And if I'm going to break there, I don't need to put a 0 in the corner. Okay, part B, state the form of the relationship between the variables. Now we know that a scatter plot can be described in 3 ways: direction, form, and strength. The direction here is obviously negative, but that's not what I'm being asked to describe. The strength looks like it's very strong as well, but I'm once again not being asked to describe the strength. I'm asked to describe the form. Is it linear or is it non-linear? Well, that's this part here, and the form is linear. That's all I would need to write to earn the mark. And that's all there was for question 19. Let's look at question 20. The graph shows the association between the air temperature, X, and the number of vehicles parked at a train station, Y. So what we're seeing here, that as the temperature increases, the number of vehicles grow. So we've got a positive relationship, and they've given us the equation. They've told us the R value and the R squared value. The question now asks us to identify Pearson's correlation coefficient. Well, we know Pearson's correlation coefficient is R, so it's 0.986. They've put both on there to see if you understand the difference. R squared is the coefficient of determination. It's not the same as Pearson's correlation coefficient. So the value is R. And we use that to describe the strength of the association between X and Y. And we can see that because this is very close to 1, that it's going to be strong correlation. So all I need to simply write there is Pearson's correlation coefficient is 0.986. So because I've correctly identified R, then I get my first of 2 marks for this part of the question. If I'd chosen R squared by accident, or because I simply didn't understand the difference between R and R squared, then I'm not going to get this mark. Okay, the second mark, using it to describe the strength. Now, I would say that there would probably have been some students who started the question but didn't read it fully and missed this part here. So using it to describe the strength, got to read those questions carefully. We can describe that strength as strong, and we get our second mark, correctly describing the strength as strong. And there were some notes in the actual marking scheme that if I had described R squared, I could still get this answer here as long as I'd used R squared to make that decision. If I had just said it's strong and I had not used R or R squared up here, I'd skip this part completely, or had picked something else as my correlation coefficient, such as the equation, then I could not get the second mark. I had to actually pick one or the other to get the full second mark. Okay, part B is worth 1 of the 4 marks. Define confounding variable, and it's suggested that the time of the day is the confounding variable in this situation. Now, if we think about the actual context carefully, I'm wanting to go to the train station and park my car there for the day. Now, do I make that decision based on how hot it is outside? Do I say, I feel like taking a drive to the train station today because it's 40 degrees, I think I'll go and park my car there. No, people don't make their decision to park at the train station because of the weather. They make a decision to park at the train station because they need to go somewhere on the train. And most people are going to work. So the time of day, or the day of the week even, is one of the reasons why people go to the train station. And obviously, as the day progresses, the train station gets more busy. So this whole thing about the air temperature, yes, we would see as the day progresses, the day gets hotter, and as the day progresses, more people are parking at the train station. But the air temperature is not what's actually having the effect on the number of vehicles. It's a confounding variable in this situation. It's actually the time of day that's not being graphed, and it's the time of day that's what's causing both of these to increase. So definition of a confounding variable is an external, unmeasured variable, so it's something that sits outside the scatter plot, and it impacts or has an effect on either just the response variable or even both variables. Now, to do this, to get this mark, I had to correctly define confounding variable. Now, this is a textbook style one. Obviously, if the markers were marking this, they'd probably see tens of thousands of completely different answers, and I'm sure that what they were probably looking for is this key part here, impacts or has an effect on either the response variable or on both. And if you look at the notes on the external marking guide scheme, it's got these keywords in there, impact and effect on one or both. And this other bit here, the external unmeasured variable, that's also important because it's not actually part of the graph. So part C was kind of where I got to earlier in my explanation of the confounding variables. Why is that time of day a confounding variable? Well, here's an example in writing. The time of day affects the temperature. As the day progresses, it gets hotter towards midday and cooler towards the evening. the time of day affects the number of vehicles, there'll be more cars during peak working periods of the day. So now I've explained why time of day affects both air temperature and the number of vehicles. And to get the mark, you had to actually talk about both. So there was a bit of work there for one mark. So we've correctly explained why T could be a confounding variable. Well, that's the 2 questions in the paper on bivariate data. If you have any question about those or confounding variables or anything you want to get some clarification on, you can email me at mcclutchymass@yahoo.com. Well, you've been watching McClutchy Mass. I'm Natalie McClutchy. Have a wonderful day.